Julia mentioned, my name is David Stokes. I'm with Jeffrey L. Bruce and Company. We're based out of Kansas City, and we also have a smaller office in Des Moines as well, West Des Moines. And we're a little bit unique when it comes to what we do as landscape architects. We do the traditional landscape architecture, design and planning, but we also really have a strong focus on integrated water management, green infrastructure, green roofs, urban soils, and providing those specialized services to larger, more national landscape architects. So we get the opportunity to work on really, really complex projects throughout the country, and this is basically a presentation that kind of shows you well, we're gonna go over one particular project in general here in Kansas City, and then I'll just kind of show you some images of some other projects we've done throughout the country. But I think what you want to try to pull from this is just the complexity, the level of complexity and coordination that's required when these designs are being built and implemented in the field. And you get a greater appreciation once you've gone through a few projects that have been constructed. Because it's one thing to design a project, but it's another to see it through to completion and actually getting it constructed. We do parks and recreation planning, water resource management, green infrastructure, agronomic and soil engineering. We do sports master planning, operational maintenance planning. So as part of the specialized services and what I'd like to talk a little bit about today and focus on today is green roofs. This is a project in La Jolla, California at the NOAA facility there. And really what this is this is an extensive roof. And you'll see by the diagram in the upper right, it's the layered system that I'm sure you guys are all aware of. According to Julia, you guys have been kind of going through the anatomy of a green roof and different types of things. So this shouldn't be any new information to you, but it's important when you get kind of to the top layers of that profile, based on where you're at in the country, or the world for that matter, as to how that soil is going to perform, because really below the soil mix or the soil media in that profile, the rest of those components are very, very predictable in their performance. However, the soil is not. It can be, but it often is not. And when we talk about extensive roofs, there's three big manufacturers of these products. There's American Hydrotech, there's Henry, and then I can't think of the other one right off the top of my head, but they all try to sell a system of these products. So instead of selling these individual products, which they also do, they try to sell this layer cake in a system. And oftentimes what I kind of take issue with is the soil mix, because they just don't have the level of quality control that us in this office often try to implement on projects. So, you know, with that, I'm not going to get into the great details and how they're kind of missing the boat on soils, but just wanted to make you aware that they do sell systems, and I really have no qualms or quarrels about each of their individual components below the soil, because they're proven over time and they're performance driven, but oftentimes the soil mix and the plant material above it kind of take a back seat, and it's kind of whatever's available at the time what's delivered to the site, which we try to avoid. Here's another project in Kansas City. This is the 909 Walnut building. which is, like I said, it's in downtown Kansas City, and it's on top of a 9-story parking garage. And the large building that's just beyond it in the distance, that's a huge condominium building. And the residents of that building actually enjoy this space as an open park. And so you can see over time it's matured very well. And it's an interesting project because it utilizes a whole host of materials below the surface that make this install successful. There's obviously soil for the plant material, but we utilize lightweight foam to bulk up the system. And we had to do that because of the loading parameters that were required on this particular roof. And I'll get into a little bit more of that in a little while here when I talk about the other project here in Kansas City at the Kaufman Performing Arts. Other specialized services, I spoke about water resource management and harvesting. So on site, we, on all projects that we undertake, we're always introducing the idea of harvesting water and reusing it. So what we try to do is harvest the water in some type of cistern or containment system and then reuse that water in the irrigation system. And even in some cases, in some of the more highly urban areas, if we're harvesting more than the irrigation system will use, we will actually use those systems for evaporative cooling through dispersion systems where it's actually spraying a finer mist and releasing it back into the atmosphere rather than dumping it to the city storm system. Water resource management and harvesting, once again, is another service we provide where we start to develop metrics for harvesting of stormwater in certain storm events. And this is specifically for the purpose of water, or I guess peak flow reduction, reduction of water volume going into water velocity going into the city storm system, and then obviously reusing irrigation. This is something we always, this graphic is getting a little dated, but it really tells the story of what we try to do on sites with rainfall and how that really interrelates with the green roof system and some of the building energy and maintenance systems. On larger buildings, we like to not only collect the water that's coming off of the roof because it's of a relatively high quality, but there's lots of condensate that often gets dumped into the city storm system. Condensate that's coming from the HVAC system of the building, the heating and air conditioning system. And that's really, just when you really want to break it down, it's just clean distilled water. And so we try to harvest that and channel those, what I would consider to be waste streams, into a cistern storage tank and reuse it in the landscape in some fashion. Whether it's through irrigation to support plant life, or if it's something more elegant like a water feature, something that animates the water on the site. It's another way to look at the integrated water cycle and just leave it at that. I really didn't talk much about gray water or black water, but we also try to, if the budget allows on a project, we will take gray water and potentially black water from a building, run it through a series of pretty extensive treatment, filtration and treatment packages, where we can clean the water enough to reuse it in the landscape to a certain degree. Some municipalities throughout the country won't allow you to do this. More of them are really heading toward allowing gray water to be reused, but black water is still still kind of out there a ways, but it's definitely moving in the right direction. And then comprehensive soil design and analysis, just trying to understand how water's moving through the soil, how airspace and pore space affects those soil profiles. And you'll see, and this is just a detail that we developed for a project. I think this was a project in New York, where we, in the upper left-hand corner, where we have soil moisture sensors that are tied to our irrigation system. So what they do is they inform the irrigation system of what the volumetric moisture is in the soil, and if it falls within the sweet spot of field capacity or wilting point, the system can be allowed to run as normal. But as it reaches field capacity, you want to shut that irrigation system off, because you get beyond field. Actually, if you've reached field capacity, water starts to run off of that soil, and you're basically throwing water down the drain. On the other hand, permanent wilting point, you also want to set your parameter on the soil moisture sensor to kick the irrigation system on as you're starting to reach that permanent wilting point, because when it gets to the wilting point, it's too late, and the plant starts to desiccate. But so we're tying those soil moisture sensors into an automated control system for the irrigation, which truly makes it a smart system. Here's kind of a nerdy, geeky chart, and it's more generalized. We have much more accurate charts than this, but this gives you an idea of, based on soil texture, sandy loam, clay, and heavy clay type of soil. This is the field capacity level that we're looking at, and we want to make sure that when our soil moisture sensor tells us that this range when telling us that the sensors are getting close to this range, we want to make sure we're shutting that system off so we're not wasting water. On the other hand, on this column with permanent wilting point, this is where we want it to turn on so we can save the plant. So this chart over here kind of illustrates permanent wilting point field capacity as it relates to the soil moisture potential on the left-hand side, and then volumetric moisture in the soil, which is on the bottom side of this chart. So getting to the fun part, this is the Kaufman Center for the Performing Arts here in Kansas City, and this is a project that really implements almost everything we do in terms of soil design, irrigation design, and how that relates to how you install it on a greenery, because the vast majority of this site is actually on structure. And can you folks see my pointer and how I'm moving it around?
Yes.
Okay, good. So on this site, so this is downtown Kansas City. This is Broadway Boulevard here. This is Wyandotte. And essentially, on the north side of this building, which is, you can't see, it's kind of obscured by the building itself, this is a green roof profile that has about a 12-inch soil depth on it. And then as you wrap around the building on both sides, come off of structure, and you're essentially on a relatively steep slope, 2.5 to 1 slope on both sides. And then there's a drop-off / entry drive cutting, basically bisecting the site in an east-west fashion. And then south of there is what's called the Arts District Garage. You're asking yourself, garage? Well, this is essentially a public park on top of a parking structure. There's about 3 to 4 stories, depending on where you're at. There's 3 to 4 stories of parking garage underneath this park setting. And so presented a lot of challenges in terms of how we procure and install soil on this site. So we'll just move forward, and I'll start talking with you about some of the challenges we faced as we had to coordinate with other disciplines and even just coordinating in-house within ourselves. So as we cut a cross-section to this site, the north side of the building, which I was referring to before, this is a green roof that, since it's a cricketed roof, which means there's peaks and valleys that go to drains on the low point of each of those peaks and valleys. The soil ranges from about 10 inches to about 12 inches of soil. So that's, in our estimation, that would be considered a semi-intensive type of green roof profile. And it's not what we would consider a heavy intensive, but it's a semi-intensive roof. And we're growing large, well, not large, but taller ornamental grasses on the north side of this facility. So we'll come back to that in a moment. Here's that entry drive I was talking about, and like I said, we're cutting a section almost halfway through the site. And you can see here where the park-like setting is on top of the parking structure itself. And what we had to do in this case, since the garage is actually sloping to the south, we had to bulk it up with foam so that we had a relatively flat surface as the lawn space for the park setting. And then the southern wall of the actual parking garage is here. And then just south of there is where we have stormwater, rainwater harvesting tanks. And really what this system is designed to do is take every drop of water on this site and pull it into that storage tank, and then we reuse that for irrigation on the site, because all in all, it's probably with the garage roof, I keep calling it the garage roof, it's a park, but the garage, the park on top of the garage is about 2 acres. It's a little over 2 acres. Then as you wrap around the side and along the north side, you're adding about another 1.5 acres. So it's well over 3 acres. It's approximately 3.5 acres of land, which you wouldn't think is a whole lot, but for Kansas City summers, when irrigation peak demand is at its highest during the month of July, this storage tank really takes pressures off of the city's domestic water system. And the actual Performing Arts Center is starting to understand and realize the savings that come with that by taking that irrigation water off the grid. So getting into some of the details, this is actually on the east side of the facility, and there's large retaining walls. And since we're dealing with a lot of slope in the wintertime, when soil starts to frost up and start to freeze and develop a crust on the surface, you could get rain events when that phenomena is occurring. And so what we needed to do was plan for drainage behind these large retaining walls. And that's what you see in these photos. This is a fairly lengthy trench drain. You would typically find these trench drains in pavement situations, but because the landscape is so vast and there's that potential for water to pond up there, we needed to have a way to relieve that water against the backside of that wall. So this took the coordination efforts of ourselves in terms of the soils and drainage design, the lead landscape architect, because they wanted to have an element that would disappear in the landscape and not stick out like a sore thumb. And then obviously the structural engineer has to make sure that the fact that we're bolting this into his retaining wall here, we need to make sure that all the structural parameters have been met and that it's properly anchored that wall. And then not only that, but on the back side of this wall, and you can't see it, but there's waterproofing on the back side of that wall that we also had to interact with. So you can't just bolt an element like this that's taking care of drainage. You can't bolt it directly through waterproofing. You have to coordinate those waterproofing details with the structural and, in some cases, the mechanical engineer as well. And I think on this one, we also had to do a little bit of coordination with the plumbing engineer, because as we took these pipes down vertically, we had to tie into some of the other drainage that was occurring further down in the profile that was actually taking foundation water away from the building as well. So we had to tie into those systems, which makes for a very complex network and spaghetti system of piping. So on the site, there's, I can't remember the actual number of trees, but it's in the hundreds, almost probably approaching close to 1,000 trees on this site. And in order to keep everything straight, we needed to code these and put tags on each of these trees and really indicate root ball height, because depending on where you're at on that site, needed to be a little bit shallower with the root ball, and if not, you have root balls sticking out of the ground, which creates all kinds of other problems when you're trying to implement pavement, either on top of or adjacent to root balls. There's also, as you move down a slope, as we had to cut tree pits or the excavation trenches to put the trees into, we needed to really take into consideration the root ball height, because you can't plant a tree perpendicular to the slope. You have to plant it vertically. So you needed to plan for what's going to happen to the soil just upstream of that tree and what's happening on the downhill side of that as well. And so we have some instances where there's maybe a little bit of a notch of root ball that's actually protruding out into finished grade, because you can't bury that root ball, but you also can't have it setting all the way out of the ground. So we kind of had to balance that equation. And here's some photos of those trees in process of being installed. So because of the size of the trees, they needed to crane them up to the top of this slope, because what they were discovering is that the bobcats that they were using to try to pull those trees or push those trees up the slope, they weren't getting enough traction, and there wasn't enough weight to allow them to successfully move those to the top of the slope. So in the upper right-hand corner, you see them kind of craning them into place. So this is on the east side of the building, of the center, and you can see just the sheer amount of slope that's on this facade. What's happening is there's about a 2.5 to 1 slope, which in traditional landscape architecture terms is a slope that's next to impossible to maintain. So what we needed to do was create a situation where the slope would allow for the soils to be installed properly on them. And what we utilized was this product called GeoWeb. It looks like a honeycomb system of black plastic, essentially. Well, when this comes off the truck, it's essentially folded up, and when spread open, it kind of spreads open like an accordion. And that's how they installed it on this slope. And you can see where we had to install trees. We had to cut some of that GeoWeb away so that we can fit the tree into that slope system. Now, you can't just lay this on the slope. It has to be anchored up at the top of the slope. And in this case, we used a series of subsurface concrete curves that we had to eye-bolt and anchor into place based on the loading weight of the soil, because the soil is going to produce a pull and a force that's going to try to move that GeoWeb. And when you get all those cells filled with soil, it's amazing the amount of weight that system starts to take we needed, and we as landscape architects did not size those concrete curbs. We had to work with the structural engineer and the civil engineer in this case to say, hey, okay, here's the length of our slope, here's the height of our slope, and here's the saturated weight of the soil. What they did was they developed, or I guess they plugged it into their own equation to determine exactly how much weight that those curbs need to actually hold up. So that's something that's really important when you're talking about putting soil on slopes and slopes on green roofs as well, because if you don't have the proper documentation and something fails down the line, all of a sudden the finger gets pointed in every direction. So at that point, the civil engineer is liable for a failure, the structural engineer is liable for the failure, and to a certain degree the landscape architect is as well. So it's very important in that process, and we took very, very intricate steps to make sure that the proper documentation was had, and that all the conversations were documented so that if something were to fail, that we did our due diligence. And this slope is holding up very nicely for us so far. This is one of the slopes on the upper right-hand corner here. This is one of the slopes that is on the west side of the facility. It almost mirrors the other side of the facility, but we had to really bench in some of these tree pit locations. So you see notches. So this is a planar surface that I think this is more like 3-to-1. But you see the planar surface, and then they've notched into that soil. And this is where the location of one of the trees that was planted there was installed. And we had to do it that way because of, and you'll see that there's varying sizes. That's really dependent upon how tall the root ball was. So when the trees were tagged out in the nursery, we had to take measurements of those root balls so that we could direct the contractor as to how deep to make those notches.
David, is that a manufactured soil that we're looking at, or is that a native soil?
No, that's a great question. This is not manufactured soil. This is basically subgrade.
Okay.
And so all the soil that will be involved in this install is actually going to be veneered on top of this. So this is basically acting as our compacted subgrade.
Okay, thanks.
Here's some more finished photos where you start to see the top of this slope, and this is where they were just really starting to unfold all of it and get it ready for the excavation of those, what I'm calling grade beams. They're basically the footings, concrete footings that hold all of this system up. This is on the uphill side, on the east side of the building. This is actually looking north. But you can see where we had to cut around some pretty significant tree planting. And you'll see, if you look really closely, there's little gray or silver little pieces in between here. Those are actually tendons that are holding these pieces together. So you'll see a bunch of these gray pieces. And then if you come down, you can't see it in this photo, but there's also gray pieces coming along down this road. And the width between those is actually the product itself, and that's how it accordions out. And then when that's snapped together, then what they do is they pin it into, along with the footing that they build on the top side of the slope, they will actually pin it into subgrade, which this is the subgrade surface. They'll actually pound pins down into the ground. And I believe they go about, it depends on what the design is, but I think in this case it was that they were pounded about 36 inches into the ground. And what that does is it's just a secondary anchoring system that allows it to stay in place while the soil is being placed into the cell. This is a nice photo showing that the slope is actually almost covered with geoweb at this point. And you can tell that there's pretty significant cutouts for the trees. And you can see on the downhill side where the root ball is kind of protruding out, and we had to feather that soil back once we got to that point. The soil work wasn't installed yet, but since the root ball is sticking up on the downhill side, we really had to feather grade out on the downhill side of each of the trees. This is showing, on this lower right-hand corner, this is showing a mock-up of the plant material that was going to be going into these cells. And we needed to determine whether or not, and it was also a cost consideration, whether or not we wanted to put a potted plant in each of these cells or every other cell. And by the time all was said and done, they actually ended up putting plant material in each one of the cells, which I found quite amazing because it was quite an expensive little detail. But it's immediate impact. When you get vegetation into these voids, into these cells, you're immediately anchoring and arming that slope so that you don't get any slough off soils. This photo on the upper right-hand corner is the actual design soil after it was placed into all these cells within the GeoWeb. So that's what it looks like after you fill it with soil. This is not necessarily related to soils, but it's just indicating there's a lot of elements, architectural elements, that we had to deal with when trying to set the material. So this is on the north end of, I guess this is the north end of the garage wall. So this is actually off structure, but this cabling system that ties into the building really had to be coordinated not only with at-grade situations, but how it affected what was happening over here, because as we installed these precast stair pieces, we had elements of that happening over here as well. And in this case, we're actually installing it on top of roof deck, that is, or not roof deck, but on top of concrete surface. And on the other side of the wall, we had to install it on top of roof deck. So we had to bulk it up with foam, and in some cases we had to shim it up with sand setting bed on top of some of the structural elements that occur over on the actual garage roof itself. Here's some photos of, so this is that slope, Julia, that you were asking if that was the design soil. This is the area where now is soil is installed, the plant material is installed, and it looks like, yeah, in this case, the mulch was also installed on the slope. But you can start to see how it takes shape after the soil gets veneered on the slope, and then you start to install the plant material. It starts to really give it, you know, a soft quality, and you can tell that just by the sheer spacing of the plant material, it's really starting to hold the slope and mitigate any sort of erosion potential that would occur on that slope. And then these other photos are just illustrating installed plant material. This is probably, I would say, probably 2 or 3 weeks after the installation of the plant material.
David, would you pause for a moment and tell the class a little bit about how you use biologicals in the install? Yeah. Because something we've talked about. Sure.
So all of our soils on this site are sand-based soils, and that's typically our philosophy on designing soil, because when you use sand as the base component, in our estimation, and you blend, so our sand-based soils have a sand component, and then they also have an organic component, which typically comes in the form of either a well-conditioned, well-aged compost, or worm casting, which is basically worm poop. and we blend that together. And by doing so, we can achieve really predictable performance criteria in the soil. So when we develop soils, sand-based soils, we have a sand component, and we test that sand component to make sure that it's fitting our specified parameters. Then there's a compost component or an organic amendment component. We need to make sure that that's meeting our performance criteria. Once those two are approved as individual components, then we allow the soil testing laboratory to blend those components together to develop a mix that meets our criteria. So in other words, by meet our criteria, I mean it needs to be at a certain infiltration rate. It needs to have a certain level of organic matter content. It has to have a certain bulk density, which is essentially compaction, dry compaction. It has to have certain water retention and water release properties. And then it also has to have a certain level of pH that we specify. So once we get to that point, and we get to an approved soil mix that the lab has prescribed. So in other words, let me back up a bit. When we get the approved sand-based component and we get the approved organic amendment component, we have the lab run a mix. And if it doesn't meet the criteria, we have them run another mix. And typically it comes in the form of 25 pounds of compost per ton of sand as one ratio. If that's too light in organic matter and the infiltration rate is still too high, we'll have them blend more organic matter into it. So it'll be like a mix of 100 pounds of compost per ton of sand. And they'll retest that. And it's kind of a coordination process to make sure we're getting the right soil performance before the contractor delivers a bunch of it to the site. Because once it gets to the site and it gets put on site, if it doesn't meet that performance criteria that's specified, we have the ability to reject that and have them take it off site. We try to avoid that at all costs because it doesn't do anybody any favors. So we do all this work up front. So you talk about a sand-based soil. Sand is essentially, it has no biological value. It's essentially a sterile material. When you blend organic matter into it or compost, you're starting to breathe a little bit more life into the soil. But from our standpoint, it's really just hitting the minimum of our performance value. So on projects, we specify biological amendments, organic and biological. So in other words, we have a liquid foliar product that we actually drench the soil with immediately after the installation of the plant material. That product is called Vermiplex. It's a complex compound of microorganisms along with high mycorrhizal populations. So what it does is it boosts up the rhizosphere of the plant material on site. It's creating beneficial relationships that when you take a sand component and an organic component and you blend it together, those biological organisms need to reassociate with one another, and that's what this liquid biological amendment does. It starts to develop a relationship between the beneficial microbes and mycorrhizae in the soil, and it creates these stronger rhizospheres, or the really fine root hairs that you see on plant material. And so it's important because those fine root hairs are the ones that are going to, those roots are the ones that are going to uptake the most nutrients and moisture within that soil profile. I think it's a misconception that whenever you see a diagram with a tree on it and there's a big tap root and there's some big lateral roots coming off of that tree, those roots aren't the ones that are taking up all the soil larger roots are there for stabilization of the tree, for lateral stabilization, and to really peg it into the ground. So we use the liquid inoculant, the liquid biological fertilizer, which we call an inoculant. And then in concert with that, we also use a granular component called NutriCat. And that's also a biological component that's actually activated by the vermiplex. So these organisms start to, for lack of a better term, they start to have a party. Then they develop into these large colonies and large populations. And what it does is it establishes a biological city in the soil, for lack of a better term. It establishes a biological community that would not really be there if you didn't have that component. You know, there's still that source of nitrogen and carbon that's being provided by the compost or that organic amendment, but the biological microbe component is not there unless you breathe life back into it. And that's why we use the liquid biological inoculant, and we also use the granular as well. There's all kinds of products. There's all kinds of products out there that really boost mycorrhizal populations. And I would encourage you to do a little bit more research and really learn more about the differences in products, because they all have benefits in their own way, but we've found a combination that works for us. So this is in the upper left-hand corner. This is on the north side of the facility where we had that 9 to 12-inch profile. And this is what it was like probably 2 or 3 weeks after installation. And these bottom two photos, even though it's not in that same location, this is essentially what those grasses look like after one season of growth. And so you really start to see the benefits of the biological amendments that we added to the soil. And this was just another photo of in process of them installing ground cover, not only on some of the flat areas but along the slope. So this is I spoke about water harvesting on the south side of the site. Essentially what we've done here is we've implemented two 44,000-gallon cisterns, and that's where all the drainage, whether it be stormwater or water running through our soil profiles on top of the garage, that's where all of this water is going. And what we did was we manifolded these tanks together so that they're always equalized in terms of the amount of water that they have in them. But you can see along the bottom here that there's some pretty significant concrete curbs. And this is actually the anchoring system for these tanks. Because there's a high water table on this site, or a relatively high water table with casual groundwater, we needed to anchor these tanks in place because it's amazing the buoyancy that these tanks have if there's lots of groundwater present. And by buoyancy, I mean if we didn't anchor them into the ground like this, they would essentially float up onto the surface. And they would, if the conditions were right, they would bust through soil and they would just kind of float to the surface. So that's why we had to anchor them in place. But these are both essentially 44,000-gallon tanks. This is photos. These are photos illustrating the waterproof membrane that was in place on top of the garage before they started placement of soil. In this case, I think what they're doing is they're performing a flood test on this, or they just finished performing a flood test of a certain section of it. Whenever we do a green roof project, we always recommend and almost we try to mandate that they have some sort of flood testing. And what that does is it tracks and documents if there's any microscopic breaches in the membrane. In other words, small little pinholes in the membrane. The photo on the left, or on the right, I'm sorry, is the start of the foam bulking installation. Because of the nature of this parking garage structure, it's precast concrete, so there's a predetermined load that's required to go on. I mean, can't exceed the load that's going above it, which I think Julia said you guys are going to talk about probably in the next coming weeks or so. But the load requirements on this structure, when we balance that with our soils design, it forced us to bulk up the structure with some lightweight bulking, and that's what this white foam is. So in other words, to get the elevation we needed to, we couldn't fill that entire profile with soil because of the sheer weight, the saturated weight of the soil. We had to bulk it up with some of this foam so that we could get soil profiles in there. I would say over the vast majority of the garage roof, we have a profile of about 9 inches of sand-based soil that turf is growing on. But you'll see there's trees on the roof as well, and those trees themselves require a deeper profile of soil. So we needed to strategically locate those trees over vertical columns in the structure so that they could handle the weight. And in those cases, we were also allowed to beef up the volume of soil that we could place in the area. So this is just it's a very interesting process because these are large blocks of foam. They kind of fit together like a 3D puzzle. And you're probably asking yourself, what's with all the tires on this photo? And really, it's to add weight to that foam because if you don't get soil or other parts of the layer cake on top of it, wind could uplift these things and take them over into the next county if the wind is right. So that's the reason for the tires. It's just adding extra weight to the profile. And you can see here, if you look closely, there's numbers and letters on each of these pieces on the left-hand photo. And it literally is a puzzle. And when we develop drawings for these, for the installation of this foam, we need to have each of these pieces numbered so that it's going in sequence and that elevations are being hit all along this garage, so that elevations are being met, the design elevation. So it's a very complex process, but so this is what we call geofoam, and this geofoam comes typically it comes in 4-foot by 8-foot blocks that are anywhere from 2 to 4 feet deep, and really they come in different densities. I think there's 3 or 4 different densities that are the most common. But by density, I mean, so if you go to the Target or the Walmart down there and you buy, let's say you're buying a kitchen appliance, that white styrofoam that's in that box, that's essentially what this stuff is, but at a much larger scale. And if you think about that, if you ever pull that styrofoam out of that box, kind of squeeze it, there's a little bit of give to it. That's what I'm referring to when I'm talking about density of the foam. There's higher densities and lower densities of foam. The foam that you find in those packaged goods, that's a really low density foam. So you can actually squeeze it with your hand. On this, you can walk on this foam that's illustrated in these photos, and there won't be a footprint that's left behind. So depending on the programmed use that this space is going to get, and whether or not you're going to be driving heavy trucks on it or other heavy maintenance equipment, that really drives the density that you want to use in the foam. Once again, you see it's a big puzzle. It's a big three-dimensional puzzle. You see here that these two pieces were angled because you're coming down a slope in this instance. Then you'll see a big void in the foam here. This is where a tree was planted. So we had to stack it in such a way that we're allowing for trees to have their own tree pits or tree excavation areas where the trees could be installed. Since this roof is irrigated and there's also sub-drainage within the profile, we had to cut trenches. And when you're talking about irrigation pipe and sub-drainage pipe, the foam manufacturer is not going to cut little notches in the foam for you. So you have to kind of resort to creative ways to cut trenches into the foam. And there's equipment out there. This, for instance, is a hot iron. This is a handheld piece of equipment that's connected to an electrical charge, and it's a hot wire, a hot bar. It's almost like, you look at the inside of an electric oven. It's that heating element that's in the oven that kind of gets to that red glow. That's essentially what this thing is doing. And this thing will just slice through the foam like a hot knife through butter. And there's different types of equipment that you can use. This is a hot iron. There's also hot wire equipment. But what this does is it allows you to cut nice, even, smooth trenches for irrigation lines, communication lines, electrical lines, sub-drainage pipe, that kind of thing. And this equipment comes in different sizes. But you can see it's really melting its way through this foam. And it's actually, it's a really neat process to see happen in the field. This orange line that you see here was a chalk line that was indicating the center line of that trench. So if you line up the center line of that trench with the center of this hot iron, it gives the contractor that's cutting these trenches a nice guide to go along. Once again, here's how we were dealing with slope. This all is on top of foam, and on the right-hand side, and you can start to see there's drainage cleanouts, irrigation heads and irrigation equipment, and all this irrigation equipment, all the piping that's connecting these pieces of equipment was notched into that foam on the previous slide I showed you. So it's a very intricate, calculated system that needs to go in chronological order. Right here is a metal edge treatment that's laying on top of the foam, because you can see some of the white foam peeking through here. This is angled steel with cross bracing every 10 or 15 feet. But this is basically the edging for a walkway that was installed, and I believe it was a decomposed granite walkway that sat on top of it. So that was a way of keeping that material contained within this walkway without it spilling over into some of the more landscaped areas. And here's a shot of, this was early one morning when they were just really going like gangbusters to get the soil onto the roof. What's interesting is they had to install the soil from the center and work their way out, because if you dump it all in one spot, the differential loading on that precast structure, on that precast deck, could deflect and crack it, and it could fail the roof. So they really had to take their time and come up with a plan on how to distribute the weight of the soil as they were installing it on the roof. This is a shot of plant material, and it doesn't look that that doesn't look that healthy, but it is. This is vegetation, and it's native grasses, taller grasses, ornamental grasses, and taller native grasses that were grown on a mat. So this is a geotextile mat that was rolled out on some of the slopes to get that immediate impact of erosion mitigation and try to get the plant material a running start instead of having individual plants kind of plucked into the side of the slope. We had it contract grown on a mat, and it was growing for, I think, a full growing season. And then it's much like sod. You cut the mat, roll it up like sod, and then you bring it to the site and you roll it out. And it took a while to snap out of this condition, but once it did, that slope was fully vegetated. I think it took probably, I would say, about 3 months for it to really start to fill in. And then a year later, you wouldn't even be able to tell that there was a mat. This is just showing some of the finished product of how that walkway was relating to some of the landscaped areas.
I have a question for you, David.
Yep.
So one of the students wants to know, why did you use the mat there instead of like the GeoWeb with the individual cells at the other slope closer to the building?
Because this was a completely different contract. The south side of the building, so the garage was one project, and the actual Performing Arts Center was another project. So where that drop-off drive kind of bisects the site, the south half of that, which is on top of the parking garage, was under a completely different contract, a completely different client. And the north side of that site was the actual Performing Arts Center themselves. So it had to do with budget, and it was a lot more cost-effective for the client on the south side to do this than it was to go with the individual plants like we did in the GeoWeb on. So it was essentially budget-driven and client-driven because they were two different clients. Now we tried talking them into doing that because it was such a success, but they didn't like the price tag associated. And that's really the main difference. When this was rolled out like this, we were very concerned because if you look at this, it doesn't look like it's going to take off.
Yeah.
But it did, and so right now they're rolling it on top of the sand-based soil, and then immediately after they had this slope fully installed, we went in with that granular application of biological fertilizer, and then we gave it that Vermiplex, that foliar drench, and it just kick-started it. Within, like I said, within 3 months, it looked twice as full as it does right here, and then within a year, you wouldn't even be able to tell that it was individual plants grown on a mat.
The question is, would you be able to do that with forbs or, things that weren't grasses?
You can. We don't have specific experience with forbs per se, but I know you can do that. It takes a client that has patience, because you really need to have at least a growing season under your belt to grow something like that on a mat. And then you also have to have whoever's contract growing this, they really have to have knowledge of the plant material. So it's one of those specialized situations where you really need to pre-qualify the contractor that's trying to grow this plant material on the mat. Good question.
Thanks.
We haven't done it specifically, but I know that it can be done. Well, I think I'm running low on time here, and that's pretty much the breadth of what I was going to present. I'll just kind of fast forward through these irrigation slides, and we had some metrics that we developed when we finished the project, and it's kind of interesting in terms of the soil-water equation on the site. So the total annual water use for that site is just over 1 million gallons, and so throughout that first year, we had really put a monitor on it. That's where these metrics came from. But that 88,000 gallons worth of storage, the cistern storage, it captured 37% of the stormwater runoff from the site. And then it had an overflow frequency of 59% and a dry cistern frequency of 16%. So what that's essentially saying is somewhere between 1/10 and 1/8 of the time the cistern was dry. So essentially most of the time the cistern was full of water. The overflow frequency was 59%. So what that means is that a heavy storm came through, completely inundated the tanks, and the water had to overflow into the city system. But when you talk about if that wasn't in place, 100% of the overflow would be going into the storm. So we saved the city 40% stormwater volume of rainwater that's falling on this site. Over that year, the cistern supplied just over 957,000 gallons of irrigation. And then it says additional storage of the engineered soil captured 41% of stormwater runoff. And what that means is, as a sand-based soil, sand, when you look at sand by itself, it has about a 40% void space, 35 to 40% void space when you look at it in profile. So in other words, whatever's not being taken up, whatever space is not being taken up by the sand particles themselves, the rest of that is basically airspace. So 41% of that was capturing runoff from stormwater, which is essentially why the site was determined the first stormwater detention facility on a green roof in Kansas City. So it was actually permitted as a stormwater detention facility. This site was, and which is a very, very rare thing when you're talking about green roofs. People don't think of green roofs as stormwater detention facilities, but they actually are. And so it was quite an amazing feat that we had accomplished on this project. Like I said before, we saved the city, that first year, I think we saved them around $45,000 or $46,000, but we're estimating about $52,000 a year in savings for potable water costs. So that's domestic water. And when you look at when you look at prices or when you look at the installed cost for the harvesting system, at 88,000 gallons of water storage, on these projects, the installed cost for a system like that is about $2. It costs about $2 for every gallon you're harvesting. So the cost of that was, I think it was around $188,000, somewhere around in there, $188,000 to implement that system. Well, that system is going to pay for itself in somewhere between 3 and 4 years. So it's already paid for itself. which is quite amazing. And then this just gives some other metrics. 100,000 gallon cistern, when used for irrigation, represents 140 tons of evaporative cooling. And these are just metrics that the city has really taken under their wing, and they've really demonstrated this space to the rest of the community. And you're starting to see lots of other smaller facilities incorporate green roofs and water harvesting into their facilities. So it's quite a movement in Kansas City, and we're starting to see it specifically on the West Coast. The East Coast is a little bit slower in reacting, but they are certainly on board with this type of technology. And then, since water costs in the Midwest are so low, it's kind of a difficult sell, but Chicago is really a champion for this type of technology of incorporating these strategies into green roofs and on site. So with that, I guess I'll just kind of open it up to any other questions. So I hope this was informative.
Actually, it's interesting because a lot of what you talked about connects the dots between a lot of the things that we have been studying in terms of the metrics. So,
yeah, you know, I think it's important when you're talking about green roof systems. To me, one of the more critical components is whenever we engage in a green roof project, the coordination between the architect, the structural engineer, and the landscape architect is very important, because when you're especially when you're talking about loading on a roof, to determine the load rating of your soil, you really need to have the soil in a saturated condition, and you need to have that documented so that you can share that with the structural engineer, and he or she can tell you, okay, based on the soil depth at that soil weight when it's saturated, we can't have 3 feet of soil here. You're going to be limited to 12 inches. And that's really going to impact your design in terms of what you grow on the roof. And so that's a really critical component at the very beginning stages of a green roof project. The other thing is that, and we kind of get a little bit out of our element because we're geeks on green roofs, but the waterproof membrane is very, very important. And when talking about leak detection and protection of that membrane, it's very important that that you try to push the envelope away from industry standard quality control testing of leak detection on the roof. Traditionally, on green roofs, you will see architects and owners really just go for the minimum value when it comes to certifying that roof as being watertight. In other words, the industry standard is to flood test it. So you have a roof with parapet walls on all sides, and you flood the roof, whatever depth you flood the roof to, but it's basically a standing pool of water. And that's all fine and dandy, but what it doesn't do is it doesn't demonstrate the really tiny breaches or microscopic breaches in the membrane. When you flood test it, the larger holes or the larger breaches in the membrane are going to show through. And it's going to become very apparent where there's a big puncture or a larger hole in the membrane. But when talking about microscopic or really tiny pinhole breaches in the membrane, you really need to start talking about electronic field vector mapping. It's called EFVM, electronic field vector mapping. What that is it's basically a trace wire that goes around the perimeter of your roof that you hook up to an electrical charge. And what it does is it vector maps that roof in such a way that you don't need to flood it, but you need to get the membrane wet. And by the fact that the membrane is wet, creates this vector field, and wherever there's a breach in the membrane, you'll be able to tell, based on that vector mapping, exactly where that breach is occurring. And it can detect, what was it, can't remember the tolerance on it, but essentially if you take a sewing needle, touch a hole in the membrane, it would be able to detect that level of.
Wow.
Whereas if you're flood testing is not going to pick something like that up.
Did you guys, I've got a question. Did you guys prepare the trees in any particular way, or did you work with the nurserymen to make sure they would make it?
Yep, great question. So we tagged the trees about a year before they were installed. And by tagging, I mean we went out to the nursery, or we went out to the farm, and the trees were still in the ground. And so there was a very critical process that we went through where we met with them, tagged the trees. I think it was probably late summer, early fall. And then we went back out when the trees went dormant, and we had them root prune each of those trees with an air spade. So in other words, we went around the tree approximately the size of the root ball, and we had them air knife it or air spade it so that it had a good root pruning technique prior to them digging it up out of the ground. Because if you go in and dig it without root pruning on sizable trees, you could kill or adversely affect a lot of those hairs, root hairs, that are uptaking all the nutrients and moisture. And so it was very critical for us to get out there early, go through the process of them air spading them. Then what we did was we worked with them and got them on a biological program for half of the growing season. So we had them adding these biological components so that they were acclimated to that, and there was a certain level of stress prevention once they dug them. And then once they dug them, they probably sat above ground for, I want to say they sat above ground for probably a couple of months, 8 to 12 weeks, somewhere in there. And all the while they were giving them biological drenches in preparation for transplant to the site. So, yeah, we had a really good working dialogue, and I think typically on projects this size, you'll see a mortality rate of maybe 10% of all trees on the site. And I think the mortality rate for this project was somewhere around 2 or 3%.
Wow.
So it was quite impressive, and it's a process I'd love to go through on all projects, but unfortunately we don't have that luxury in all the projects. But we were able to write that into the specification. The owner was okay with it.
Do you find yourself doing more retrofit designs for the green roofs or landscape on structure, or do you do more from scratch projects with the architect and structural engineer?
It's literally half and half. Without hesitation, it's 50-50. We'll get, typically on a retrofit project, our coordination with the architect is much less involved because the structure is already there. They're merely improving, in most cases, the interior of it. Where our coordination lies on a retrofit project is primarily with the structural engineer, because that building already has its own structural loading capacity. It's nothing that was designed specifically for a retrofit, so we need to work really closely with the structural engineer on those types of projects. But on a from-scratch project, I would say our coordination is equally important with the architect as it is the structural. But terms of breakdown, it's about 50-50.
Okay.
We do a lot of retrofits, yeah.
Okay. Andrew's asking about the GeoWeb and how it allows the roots to grow. Because in the pictures it looks like they're solid panels. So,
if you look very closely at these photos, you'll see that there's perforation in this GeoWeb. That's really what allows the roots to grow through. So the roots will either move vertically as far as they can go, and then they'll start to move laterally. But they will go through the perforations in this GeoWeb. And it's kind of a nice feature because not only does it allow the roots to go through there, but it allows water to move through it relatively freely without damming up or backing water up. But I think the roots growing through these perforations also makes the GeoWeb network, it makes it even stronger. So yeah, to answer your question, it grows through those perforations in the GeoWeb.
how'd you get those plants planted in the GeoWeb? Was it dirt first, plants first? You're laughing.
Yeah.
It was a process.
There was some debate about this, but they put the soil in first, and then they came in and planted the individual plants into the soil that's contained within the cells after the soil was installed. To me, I think that was probably the right way to do it, because if you get the plants in the cells and then you try to put soil in after that, I think there's larger pockets of air that don't necessarily help the soil consolidate on itself. So I think we went about it the right way, but there was certainly some debates on how we should do that. And to answer your question, we put the soil in first, and then it was quite laborious to excavate the soil out of each of those cells to put the plant material in, but they had a crew of about 25 guys out there. And, they were actually working together pretty well.
Cool. The question is, what monitoring and maintenance do you do on a project like this?
Well, we don't do any maintenance on the project, but we do monitoring. So what we will do on sites like this is we'll get into the database for the irrigation system and really have a good idea of historical data of how often the site was watered, how much water was used. On the other end of things, there's meters, there's stormwater meters that are tracking how much water overflowed into the city storm system. And so oftentimes the monitoring we do, the monitoring we did on this project is really monitoring water usage and water consumption versus how much water is leaving the site. And that gives the city some better metrics to develop projects in the future. Other monitoring we do on site is we will go out from time to time and measure, much like I was saying early on in the talk, we'll monitor soil moisture, soil temperature, soil pH, just to make sure that those systems are in balance with one another. We're kind of tracking into the realm of monitoring biological activity in soil, which is a far more expensive testing process because it's a lot like crime scene investigation forensics, because you have to, in order to track and monitor and quantify biological activity in the soil, you essentially have to do DNA testing of the soil. We haven't really implemented that on a project right now. We're playing around with it because we're a little bit new to that. But DNA testing of the soil is something we're starting to crack the surface of.
Cool.
So and it's interesting how they monitor biological populations through testing and assays. So there's a group in California that does DNA testing on soil. But the thing about that is, if you're going to test for DNA in the soil, you really need to have a baseline situation. So you need to have the client and the contractor on board right away. I guess the client or the owner on board right away to say, yes, it's okay for us to test for DNA at the very beginning, because what that'll do is it'll give us a baseline, and then from there we can really track how populations are increasing, staying stagnant, or decreasing. And that'll give us a better idea of how often we need to apply these biological amendments.
Cool. So the question is, how much research do you do versus the design/production side in terms of the office? You mean it like in terms of hours or activities of the whole?
Yeah, I'd say if you were to break it down in percentages, I'd say about 20 to 25% of the time we're doing research. And by research, I mean it's applied research on projects we're actually currently involved in. Oftentimes we will submit soils or irrigation water or plant tissue. We'll submit that for testing on projects where they're not paying for it. We're doing it on our own dime to really better understand how plant material, how water, how soil is performing over time. And not only over time, but during the installation process, how do those performance values change as you're getting heavy equipment rolling over soil that you've already added your beneficial amendments to, and there's a contractor who's careless? How do we track the performance of that so we have a better idea of how to tell them what not to do next?
Yeah.
So I would say 20 to 25% of the time we're doing some type of applied research, and 75 to 80% of the time is production.
Cool.
It used to be a lot more heavily weighted toward research, but when I first got here about 14 years ago, it would have been a lot more heavy-handed in research, and I feel pretty fortunate to have gone through that process of hearing and experiencing all that research, specifically related to soil, as we've progressed as a company. But now we have a very good understanding of our systems, and we can predict their performance pretty well, but we still like to push the envelope and scale.
Cool. Well, thank you so much for doing this, David. I realize you've got a lot on your plate, and it was just really great to be able to visit with you.
Yeah, I mean, what I'd like to do at some point, and maybe it doesn't have to happen this semester, but it'd be nice. I'd like to talk about water a little bit more. And I know I talked about water quite a bit today, but we're really pushing the envelope in terms of water and how to reuse it different ways on site, how to monitor water, and how to understand where your water is going.
I think we could probably figure that out.
And I think it applies not only to at-grade situations, but on the roof itself. And we're starting to really come into our own with regard to how we use water on site. So I think, and we have some nice information that I think would make for a valuable presentation that just focused on that. So if there's ever a need for that, we'd be more than happy to tell you about
Sounds great. Well, thanks again.
Yeah, thanks everybody. I appreciate. Yeah.